don't know if I'm going to get to a circuitry review. It's the most recent one, and I'm kind of hoping that that's kind of fresh in your brain. But electrostatics, so one of the first difficulties we ran into was so many equations looked alike. That equation, that equation, that equation, and that equation. And unfortunately, if you used the wrong equation or you found the wrong concept, on the written I gave you 0. If it's multiple choice, yes, I'll have that answer to pick from. I'll have using the wrong formula to pick from there. We said we divided our questions into 2 main types, point charges and parallel plate charges. Any equation with an R in it could only be used for point charges, where you had either a single point sending out an electric field like the invisible tentacles of an octopus in all directions, or 2 points. And I used an R deliberately for radius to help you think radius, circular, round little points. Any equation with a D in it, of which there's only one, that's used between parallel plates. An equation that has neither an R nor a D could be used in any situation, and that was these 2 here. This was the definition of electric field, this was the definition of voltage, and then we adapted it as needed. For example, electric charges are arranged in the pattern shown below. So we have Q1, which is negative 6.5 microcoulombs, and Q2, which is negative 2.5 microcoulombs, and they're 0.2 meters apart. First of all, find the force, magnitude, and direction that Q2 experiences. So this is just asking us to find a force. How did we calculate electrostatic force? This is where you have your formula sheets in front of you and you're glancing at your formula sheets, and you're going to have to play along in this little game, because if not, this is going to be really ugly. How do I calculate the electrostatic force?
Q1, Q2, R squared.
I usually put a subscripted E for electrostatic force, and I either used Q1, Q2, or big Q, little q. Here I'd use Q1, Q2. We noticed it was really, really, really similar to gravity. We said, well, if for electrostatics, like charges can repel and unlike charges can attract, and if gravity, we've only found attractive masses, is there a repelling mass? Is there an anti-gravity particle? Mathematically, we don't know why there couldn't be, except there doesn't seem to be. We haven't found it, but it'd be kind of cool. That would make space travel much, much easier, because then you'd just be able to repel yourself away from a planet somehow. Be kind of neat. What was K? It was also a constant like big G, but it was a much, much nicer one. It was 9 times 10 to the 9th. Do I put the negative in here? No. Oh, we said for forces and fields for vectors, we forget the signs. In fact, I think on your formula sheet, I gave you absolute value signs. I never used to do that. I've mellowed in my old age. So it's going to be 6.5. What was microcoulombs? 10 to the what? Negative 6. And then it's going to be 2.5 times 10 to the negative 6 all over 0.2 squared. What do you get? Could you crunch that really quickly, please? Thank you for finally getting your calculator and your green sheet out, like I've said, or your formula sheet out, like I've said several times. Dylan, what'd you get? 3.66. By the way, that's not because you used a constant. Used the wrong constant there, right? Sorry, what is it? 3.656. So newtons? Like not times 10 to the? Yeah. Okay, 3.6. Say it again, William, sorry.
3.66.
Newtons. Direction. Here I have to tell you which charge we're looking at. So I said find the direction that Q2 experiences. What direction is Q2 going to experience a force? Will it experience a force to the left or to the right? To the left? It will experience a force that way? What's the, by the way, I made this negative. So, to the right. That's not your fault. It's because the diagram, I forgot to change the diagram. So it's going to be repelled. It would feel a force to the right. How do we figure that out? Like charges repel, unlike charges attract. What else could I ask you with a similar two-charge setup and then a location. In this first one, I just ignored that, never even bothered using it. But I could also have said, suppose electric charges are arranged as shown in the diagram below. Find the electric field, magnitude and direction at point P. How did I find electric field? So we had this idea for electric field of similar to gravitational field. If you had a charge, let's make it a negative charge, it was sending out, like the invisible tentacles of an octopus in all directions, an electric field. Which way would the electric field arrows point in this diagram? Would they be pointing towards the negative, or would they be pointing away from the negative? Well, because unlike gravity, charges could also repel, we had to define the direction of the field. For gravitational field, it was always towards the center of the mass of the planet. For electric field, we said it would point in the direction that a tiny positive test charge would want to move if it could. How tiny? So tiny it didn't have its own electric field. You're going to keep blinking, you're going to make it, because those blinks are getting longer and longer. Allergies? I apologize. So the electric field lines here would point this way. If I gave you this picture, I would expect you to be able to deduce that that must be a negative charge. Okay, so let's get back to here. How are we going to do it when there's two charges and we have some kind of an overlapping electric field right there? We used, the fancy phrase was the principle of superposition, which basically says you're going to find the electric field from charge 1, magnitude and direction. You're going to find the electric field from charge 2, magnitude and direction, and then you'll add them vectorially. How do I find electric field? What's the formula, the equation that I will use? So it'll be KQ1 over R1 squared. It's going to be 9 times 10 to the 9th. Q1 is 8.1 microcoulombs all over. R1 squared, 0.35 squared, right? This won't work out evenly, unless it's by a fluke, but I don't think it will. How big is the electric field at location P from charge 1? Dylan, what'd you get?
595.
Anybody else? Can you give it to me to 5 sig figs, because I'm going to be using this.
595.
What are the units for electric field? Coulombs is charge. Thank you for playing. Collect your consolation prize at the door. What are the units for electric field? Well, you can figure it out, Michael. Look at your formula sheet and look at this equation, which is the definition of electric field. What must the units be? What are the units for forces? Newtons per coulomb. Oh, and it also turned out that volts per meter also would work, and I would accept that, although I'd also go, why would you use volts per meter in this particular situation? But yes, it's the same units, so it's going to be newtons per coulomb. Direction. What's the direction of the electric field right here from charge 1? To the left or to the right? How do you know? Because you imagine a little positive charge right there and you ask which way would it want to move because of this guy, it would get repelled. And so I would write down next to this the word right. I would repeat this for charge 2, 9 times 10 to the 9th. Am I going to put the negative in for the electric field? Nope. 2.5 microcoulombs divided by charge 2 has a radius of 0.15 squared. What do you get? If you're lucky, you're able to just backspace and edit and just change the charge and R. Colby, what'd you get? Can you, again, because I'm going to be using this, give it to me to 5 or 6 sig figs, please. Even? Even? That's a fluke. Units, Colby, newtons per coulomb. Direction. A positive would feel a force to the left because of that guy. So this is going to be left. How would I combine 1 million left plus 595,100 right? Yeah. Who's winning? A million. So what's the answer? Colby. Oh, you look so put out. Oh, typing, Mr. Dueck.
404,500.
Now give it to me to 3 sig figs. 4 point in scientific notation.
4.5
times 10 to the units, direction. If this was a multiple choice question, which it will be, I would also, of course, have, if you've added them together, so I would have an answer of 1,595,000 in scientific notation. I would probably have an answer pointing to the right, and I would also have this one pointing to the right. That would be your 4 different answers probably. Okay. What else can I do with 2 points that have something overlapping? Well, not only do they have an overlapping electric field there, they also have an electric potential there. But first, between 2 point charges, I could ask you to find the electric potential energy between Q1 and Q2. And you'll notice A and B look really similar. One asks for the electric potential energy, one asks for the electric potential at a location. So how would I find electric potential energy? How did we find potential energy between point charges? Which is what? K is 9 times 10 to the 9th. Type like the wind, my angels. The faster you type, the more we get through. Q1 is 7.5. Q2 is there. R is 0.2. What do you get? Negative? Why negative? Oh, we don't put, we do put the signs in here. You can have a negative energy or a positive energy. What was it then again? Negative what? How about negative 1.22? Units? Energy is measured in newtons? I think not. Units? For energy, come on people, units? Joules. And now you'll go, oh yeah, and feel sheepish. You should. Okay? Again, we're just going to follow on our calculator and our formula sheet. I'll print this up for you, or I'll post this online, whichever you want. Mr. Dueck, isn't B asking me to find the same thing at A as A? Is electric potential and electric potential energy the same thing? What's another word for electric potential? Voltage. How do I find the voltage from a point charge? I got 2 ways to do this. I could find the voltage from charge 1, which is going to be K Q1 over R1. I could then find the voltage from charge 2, which is going to be K Q2 over R2. Some people might say, Mr. Dueck, why couldn't you just go this divided by Q? Mr. Dueck, isn't potential energy equal to Q? V, isn't voltage equal to the potential energy divided by the charge? If I knew how much potential energy was there at location P, and I knew how big the charge that I was putting at location P was, I could use this wonderful shortcut method. But unfortunately, I just found in part A the potential energy between these two, not there. So sadly, go to it. It's going to be 9 times 10 to the 9th, 7.5 microcoulombs, all over 0.2. What's the electric potential from charge 1? Oh, 0.2 is wrong, Mr. Dueck. All over 0.35, because we're at location P. Jackie, what'd you get? I heard 192, keep reading, 3, 192,857 volts. And then if I repeat for charge 2, it'll be 9 times 10 to the 9th. Will I put the negative in? Yes, I will. Negative 3.6 times 10 to the negative 6, all divided by 0.15. I think you'll get a negative answer. How do I combine these? Do I have to add them tip to tail? Do I have to go winner? No, these are scalar. Just add them. What's the net potential? What's the potential? What's the voltage at location P?
Negative 23,925.
Okay. Now, because voltage is a scalar, if I wanted to scare you, I could give you this same question, but instead, I could just make it look yuckier. I could go like this. I could have Q1 right here. I could have Q2 right here, and I could put point P. You know what? I could really scare you. I could like put point P right there, so it's not even a nice right angle. But again, if this was 0.35 and if this was 0.15, it's the same math and the same question and the same potential right there as there is when they're in a nice straight line. That looks scarier, but it's a scalar, so who cares? What else did we do? Then we started looking at questions that involved work and energy. A proton, it's a proton. Initially at rest at point X, will have what speed at point Y? So we have a fixed charge of positive 6 microcoulombs. Will the proton be speeding up or slowing down? Because it's getting repelled. Did this question ask me to find how much work? Be obvious and say what? No. So please don't start writing work equals change in potential plus change in kinetic. However, is there going to be a change in height if I call height to the right? Is there a change in speed? Is there a yucky curvy force? How would I solve this? Conservation of energy. G. I would go like this. KE initial plus PE initial equals KE final plus PE final. This is 0. Sadly, this is not, this is not, and this is not. Ugh. Potential energy is going to be K, Q1, Q2 over R initial, and then it's going to be a half M V final squared plus K, Q1, Q2 over R final. I would not try and get the V by itself here. This is where my love of algebra kind of dies an ugly death. Instead, I would move that over, and I would get a half mv final squared equals k q1 q2 over r initial minus k q1 q2 over r final. I would crunch this. I would crunch this and get an answer. I would crunch this and get an answer. You would find that either you got a minus minus, which was a plus, or you would find that this was larger. You're going to get a positive answer. That's going to equal a half mv final squared. And then I would get the v final by itself. I would, once I had these combined as a number on my calculator, I would times by 2, divide by m. Which m? It's a proton. And square root. Oh, what's Q2? It's a proton. 1.6 times 10 to negative 19. Did you want me to actually, did we want to solve this? Because this is going to take a while. I can. Or are you okay with the setup and you could take it the rest of the way yourself? You okay? You okay? Yeah? Okay, if you see me during a flex block, I can solve it with you. We can make sure we got the right answer. Now, the other possibility is I could have had it coming in with a certain speed. It would be slowing down. I could ask you how fast it was traveling, or I could even ask you where it came to a stop. How close did it get? So then your final kinetic energy would be 0, and you'd be solving for R final, which is a bit of a pain, but doable. Suppose an electron is in an electric field pointing to the right. What direction is the force acting on this electron? North, east, south, or west? What direction does an electric field point? What does it tell us? Which way a positive would want to move if it could? So which way does this electron want to move? East. So which way would a positive want to move if it could? Is that okay? Kind of an electric fieldy concept. Also, electric field lines, the arrows point in the direction of electric field. That's which way a positive would want to move if it could. So save some of this space. Could ask you a work question. How much work is done in moving an electron from point X to point Y? Will I have to do work? Does it want to move to point Y? Or is it being repelled? So I will have to do work. I'll have to push. Why can't I just go like this? Work equals force times distance. Why doesn't that work? Force is changing. It could also be the area underneath a force versus distance graph. No graph. What's our best but most cumbersome definition of work? Work equals the change in potential plus the change in kinetic. I think here we would assume that our final speed and our initial speed are 0. We start and end at rest, so I can cross that out. What's change in anything? So this is going to end up being K Q1 Q2 over R final minus K Q1 Q2 over R initial. What's Q1? Negative 12 microcoulombs. Negative 12 times 10 to the negative 6. What's Q2? It's an electron. What's the charge on an electron? Negative 1.6 times 10 to the negative 19. And I would carefully crunch the numbers and go from there. R final, by the way, is not 0.5. What's R initial is not 0.5. What's R initial? 1.5, because it's this whole distance. And R final is not 0.5. What's R final? So you can bet that if I gave this to you as a multiple choice, I'd have those sloppy mistakes as answers to pick from as well. Okay. Are you able to take it the rest of the way on your own? If you can, great. If not, see me during a flex and I'll happily go over it. Now, what if I asked how much work it would take to move from Y to X? Technically, it wants to move on its own. If I solved it, I would get negative work because it would be telling me that the electron was losing potential energy because it was falling. It just happens to be, Maddie, falling up. Okay, but it's falling. It's losing potential energy. Charge X, positive or negative? What's the polarity of charge X, and how can you tell if these are electric field lines? Yeah.
Positive.
Are you positive? What about charge Y?
It looks like the arrows are going into it, so I'll say it's negative.
In fact, it doesn't just look like the arrows are going into it. I'm fairly sure the arrows are going into it, which says the positive would want to move towards it, which means it must be negative. So you can expect some kind of electric field line-y question on your test. A proton is initially moving to the right at 6.5 times 10 to the 6th meters per second. Wow, now you've all got me yawning. How fast is it moving at point P? Sorry, Johnny, I passed that right on to you. How will I solve this question? Conservation of energy. It's going to end up being Ke initial plus Pe initial equals Ke final plus Pe final. Are any of these 0? When is kinetic energy 0? When is kinetic energy 0? When the object is at rest. Not happening here, sadly. When is potential energy 0 for electricity? When is electric potential energy 0? Or perhaps I should say, where is electric potential energy 0? Out at infinity, I can make the question be easier but look harder by having this proton start all the way out at infinity, because then you'll be able to cross one of these out. Here you can't cross any of them out. I'm just going to do the next line. It would be a half m v initial squared plus, oops, I almost did gravity, K Q1 Q2 over R, not R squared, initial, equals a half mv final squared plus k q1 q2 over r final. I gotta be honest, there is so much typing for this question to get the v final by itself. I will not give you one this long on your final exam for 1 mark, but the concepts in the individual subparts of it are all absolutely fair game. How would I solve this? I would move this to that side. I would crunch all 3 numbers, carefully carrying them to 5 or 6 sig figs. I would combine them to get one big uber number, and only then would I solve for v final by timesing by 2, dividing by m. What's m? It's a proton square root. Is that all right? Then we moved on to plates, and we smiled because plates, the physics was much nicer. First of all, the electric field between plates was constant, which also then meant the force between plates on a charge was constant, which just made the math much, much, much nicer. It meant we could use work equals force times distance if we needed to. It meant that we could use F equals ma and find A fairly easily. So a proton enters a series of charged plates. What's the impact speed on the last plate? Is this proton going to speed up or slow down? How do you know? This is negatively charged. I realize that there's some positive charge here, but overall, this is negatively charged. How are we going to solve this? Is it asking how much work? No? What's it asking? Is there a change in height if I call this height? Is there a change in speed? There isn't a yucky curvy path, but I'm telling you, this is a job for conservation of energy. I'm going to start out by going KE initial plus PE initial equals KE final plus PE final. Are any of these 0? We said that mathematically this proton moving sideways is the same as lifting an object off the ground and just having it hit the ground. In other words, the ground is right here. The final potential energy is 0. Yay! It's always nice when something cancels. So the kinetic energy, that hasn't changed since physics 11. It's going to be a half mv squared. So a half mv initial squared, a half mv final squared. Potential energy, why can't I use, don't write this down, k q1 q2 over r? It's for point charges because of the r, this is plates. Also, how many charges does this question need? Be obvious. How many charges does this formula need? 2. How many do I have? How many charges do I have? 1. It's a proton. So, no. How else can I find potential energy in this unit? Yeah?
You have the change in voltage times the charge.
And we wrote it this way. QV. Because I was trying to get it to look kind of like MGH. I'm trying to put the Q wherever the M appears in gravity because there is some mathematical similarity there. In fact, we said this was the equivalent of height. The only reason there isn't the constant G or some equivalent in front of it is because when we defined volts, we happened to work that constant into our definition of volts. So we don't need to bring in acceleration or whatever. Okay. Now what? Here, I usually chose to go times by 2, times by 2, times by 2, because here the 1/2 and the 1/2 cancel, and we ended up with this. mvi squared plus 2qv over m equals vf squared. And then we said, how do we get rid of a squared square root? That's about as complicated an equation as I'm still willing to get the v by itself with. What would I use for m? It's a proton. What is the mass of a proton? Times 10 to the negative 27. V, Johnny, you got me doing it again. V would be 5 times 10 to the 5th. Don't forget the squared. Q, it's a proton. What would the change in voltage be here? Look very carefully. This is the tricky part of this question. What is the change in voltage? 7,000. We start at positive 500, we end at negative 6,500, and so the change in voltage, or as we like to call it, the potential difference, is 7,000 volts. This was also the equation where I introduced the wings because we had lowercase v and uppercase v. Come up with your own system, but figure something out. Okay. I'll let you crunch that on your own. I just know the answer is going to be bigger than 5 times 10 to the 5th. What else? You could also find the electric field between parallel plates. So this says, what are the magnitude and the direction of the electric field between the parallel plates shown below? So here are the plates. Oh, electric field is easy. Electric field is KQ over R squared. Why is that not going to work? Point charge. What was our other way of finding electric field? Oh, I can tell you the voltage between here from now that I solved circuits. It's got to be exactly how many volts? Got to be 400 volts divided by 6 times 10 to the negative 3. What is the electric field between these plates? Could you crunch that for me, please? Yeah. Quickly, bunny. Sorry? Yeah, you're going to get 4 divided by 6. You're going to get 6.6 repeating, I think, in something else. Units. Now, I would take newtons per coulomb, but what would be the more appropriate units to use here? Your hint is it's staring at you in the equation. Volts per meter. Direction. Left or right. We imagine a little positive charge right there, and we ask which way would it want to move if it could. Look at the battery. What? Yeah, because I think this is going to end up negatively charged. This is going to end up positively charged. And so like charges are going to repel and unlike charges are going to attract. Yeah.
I think it's 66,000.
We're missing a 0?
Yeah, no, it was 66,666. I mean, so
Thank you. Yeah? Why didn't you correct me?
I just think that was...
Yeah, you didn't know a lot of things. What direction?
Yeah.
Right. Right? Right. Other nice things we could do between plates. We also said we could go F equals MA, QE equals MA. Where did that QE come in for force? Your second equation on your formula sheet where I defined electric field as the force newtons per coulomb, I just got the F by itself. And this gave you some nice options, especially if for electric field you plugged in V over D. You could find an acceleration. You could find all sorts of stuff. I didn't get to momentum with you this year, but you actually could get an MV by itself, and you could solve for the momentum of the object even if you didn't know the mass or the speed of the object. And that's one of the things that we look at in particle accelerators and collisions, is we know what the theoretical momentum should be of an object. And so when we measure the momentum, oh, we know it's not that one or that one or that. Oh, it must be this subatomic particle, because we know what its theoretical mass and velocity was supposed to be. A proton has an initial speed of 6.3 times 10 to the 6th. How fast will it be traveling when it emerges from the plates? How am I going to solve this? Is it asking how much work? So I'm not going to write work equals change in plus change in. Yeah.
Oh, no.
Oh, I thought you had a suggestion. Conservation of energy. So I'm going to go KE initial plus PE initial equals KE final plus PE final. I'm going to argue that the final potential energy here is 0, because this is like it's fallen to the ground and then just kind of kept going in a straight line at a steady speed, but it's used up all of its potential energy. Kinetic hasn't changed. It's going to be a half m v initial squared plus, what am I going to use for potential energy here? What was that? I heard someone whisper it quietly. Yeah, I'm going to use, again, QV. This was the equation that had the V and the V in it. Equals a half M V final squared. Again, I would probably choose to go times by 2, times by 2, times by 2. The 1/2 would cancel. Divide by M square root. What's the change in voltage here? 8,000. Okay. That is a really quick review of electrostatics. I hope. I think. Okay. There is about 25 minutes left. So for the remainder of class, you can ask me any questions you want to from the study guide. I gotta be honest, that final exam study guide that I gave you, the multiple choice has some nasties on it because I was trying to find tough questions and I didn't realize that many tough questions would make up the bulk of it. So if you're finding it tricky, you should. There's some nasties on it. If you're looking for good practice as well, remember you all have ultimate reviews for each unit. I have blank copies online. If you go to pitmath.com, and if you click on Physics 12, and then have patience while everything loads. First of all, sign up for a rewrite if you haven't signed up already, but here are all of the ultimate reviews, copies of them in PDF format if you want to just practice stuff. I didn't get to vector momentum this year. I didn't get to equilibrium, so the unit numbers won't match, but the topics will. And then if you want, again, a tutorial video, there's a video tutorial here on every single unit. I used to do circular motion and gravitation in one big Uber unit, so this will have both of them. The only thing is this will not have, the circular motion unit won't have the banked corner or conical pendulum because that used to not be on the provincial, so I skipped it. And it won't have escape velocity because that used to not be on the provincial, so I skipped it. But both of those are cool concepts, so I did them this year. We didn't get to Unit 8 or Unit 9 magnetic forces or magnetic induction.